Good afternoon, everyone. I'm really glad to be here. So I did my master's in this institution. I had many classes around here. And I think I'm the only one that is not a professor. I'm still a student, so I'm more close to what you are experiencing right now. And so with that, the idea of the presentation, it's going to show what I have learned mostly in the past 2 years. And I don't know, trying to show that in a very simple way. I think about 50% of the presentation is going to be something that was already shown earlier today. But I'm going to focus more on the image processing, and that field has some particularities to it. But I'm going to go through all the definitions again, because I think it's important. And I would like to invite you all to ask questions whenever you want. I don't know, there is any doubt, please. And you can ask the question in Portuguese, in Spanish, or in English, and I'm going to translate it here. I'm going to give the presentation in English. And with that, okay, so let's start with the definitions. So first, artificial intelligence, and I'm going to show some of the same figures almost, but it's that idea of enabling the machines to think or to do something that is usually attributed to what humans do, right? And that can be to do in the same way or even to do better, because we fail also a few times, and hopefully the idea with machines is that they will be more consistent than us in some tasks. And one of the words that I'm going to highlight here, one of these tasks is what I'm going to be talking about, is visual perception. So it's using computer vision, it's using automated vision, it's using a camera to simulate what our eyes do, and then using the machine to do what our brains do after that image gets into our brain and making sense of it, right? And I'm going to define machine learning in a very similar way that was shown before. I think the key word here is without using explicit instructions. So there are many ways to program a machine, and all those ways are considered to be artificial intelligence if you are trying to simulate something that usually humans do. But most of the ways, the classical way of doing that is by explicitly telling the machine to do that, right? So I have an algorithm, and I say, if, then, and so on. With machine learning, the idea is, you know, if I want to represent very complex problems, I would need hundreds of if, then, and that's not practical to do coding by hand. So what we try to do, instead of hiring a lot of programmers that would take a lot of time, we try to use the machine better and the data better. So instead of doing that all by hand, we try to expose the machine to the data and then trying to make it learn those same concepts that we would explicitly program, right? So that's the definition that I'm going to be using throughout the presentation. Two more definitions, so those were already shown also. An artificial neural network, it's a set of algorithms that is within machine learning, that is within artificial intelligence, but it's just a set of them, so there are others. And the main thing about this one is they have many connected nodes that are kind of inspired in what the brain does, so in our neurons. And what we train the model to do, it would be similar to what humans do when they are learning. So one of the things that happens is we have the synapses that are the connections of one neuron with another, and that's what we are training the model to do, right? So the stronger a connection, the more importance it's going to have in the output, and all those connections are going to make an importance to make the final prediction. How do we represent it mathematically? Because the computers are not brains. What they do mostly is multiplication of matrices, of arrays of numbers, right? So the main thing that transmits that idea of the synapses is the multiplication that is happening, and the parameters that we're going to learn are the weights of those matrices. And it's saying the rest of it. Now we go to deep learning. So in the way that neural networks are designed or are represented, it's usually a set of neurons that are in the same, in a same structure. There is a layer, and all the neurons within that layer, they are going to interact with the ones in another layer, the layer that came before it. But usually there is no interaction between them in a standard feed-forward network. So there are some special types of networks that do have interactions within the layer, but for the ones that we are going to talk about today, we are going to assume that everything inside a layer, it's kind of independent. It doesn't depend one of the other. It just depends on the layer that came before. And the whole idea with deep learning, so the deep part of it is because instead of having a conventional architecture that you have an input, a hidden layer, an output, now we have 10 hidden layers. Sometimes we have 100, sometimes we may have 500 hidden layers. The more layers you have, the more complex things you can represent. Why it only happened now and not 50 years ago? So artificial intelligence is something old, but we didn't have the computer power, and we didn't even have all the math developed to do that. So when you do math with these numbers and you are multiplying it many, many times, if it's a small number, it's going to get so small that eventually the computer is going to think it's zero. It cannot distinguish it from zero. And so if I multiply something from zero, everything else becomes zero. And that was one of the biggest problems. When I tried to put more layers, the machine couldn't learn, because at some point, most of the weights are going to become either zero or infinite, too big to be represented, and the learning process would break. So that's the main thing that happened in the last 15, 20 years maybe, that enable all this buzz about deep learning in the last 10 years, because of the computers that are able now to represent smaller and bigger numbers. For the ones that are going to download a program and don't know if I choose the 32 bits or the 64 bits, most of the computers now are 64 bits, and that enables us to represent a bigger set of numbers, and that is important. And the other thing is the hardware, of course, the performance. So representing it the same way that was already shown, we have artificial intelligence, and as a subfield of it, we have machine learning. There are other things here. And as a subfield of it, we could have here the artificial neural networks, and inside it, the deep learning. That's the more standard. There are some variations on that. Just another representation. So there is computer vision outside deep learning, and that's how it has been done for many years, using classical methods, so programming explicitly what is a border, what is a circle or a square, or things like that, and how do you combine those to get something meaningful. But there is also deep learning, a way to do that without explicitly writing all the rules to the computer. And just to show something here, which relates to the no free lunch theorem, and also relates to the idea of the robot that could climb the stairs and cook, and I like that one. So we kind of started artificial intelligence in the 1950s, Cold War times, trying to solve big things, to conquer the world, thinking on building an artificial intelligence here, a general AI that could perform better than a human in anything, and that failed. It wasn't possible with that technology, and many people argue that it's not ever going to be possible. Many people think it's just a matter of time. I'm not going to enter on that. But what we have when we talk about AI, right now is mostly narrow AI. So it's an AI that can do a very specific task very well, probably better than a human, for example, in image analysis. So there are these huge competitions on image recognition, and I think about 3 years ago, the best models, they can outperform humans. So when I show, I have 1,000 classes of objects, and some are very easy to get, some are blurred or something that you're not sure. When I show those images to a computer, it can get it right 98 something % of the time, while a human can get it right 95% of the time. But we were stuck with machinery in the 60–70% of accuracy for many, many years, and suddenly with deep learning, that 70 went to 85 and then to 95% in 2 years, and that's how deep learning get all this traction for image analysis, because it was a problem that was for many years considered almost impossible for machines to solve, and suddenly it can just do better than any human. So that's why it's important to discuss it here, and it's important to understand the impacts that it can have for plant breeding in general, especially for phenotyping, to look into images and extracting meaningful information from it. So let's try to show some more examples. This is a nice one because you can type this address and you can actually play with it. So it's a nice tool. It's from Tensorflow, which is one of the most widely used libraries for this kind of deep learning or for general neural networks. And they build it as a tool to teach, to show people how that works. And so I have here, you can think of each one of these as a different variable, right? So I have an x square, and other variables, other combinations, other functions applied to that x. And I have chosen here one of the patterns that I want my neural network to be able to represent. And you can think it as a regression or as a classification problem, right? Let's say it's a classification, so I want to know if it's blue or orange. Those are the colors of Illinois University, just by chance. And you can see that this pattern, by chance, it's very similar to this one that was already in the inputs, right? And so it's kind of easy for the model to learn. After a few epochs of training, you see that these lines, they represent the weights that are given to those connections. And that's similar to what happens in our brain. And you see that the lines that are coming from this pattern, they are stronger, right? So they are more related with the output. And then you can see some intermediate outputs. So that's the whole idea of the power of the model to model complex interactions and things, or complex features. Because in these intermediate steps, I have combinations of all the inputs, and you can see that this one and that one are stronger, and then all of them are contributing to the final ones, and you can see that they start, even in this layer, they start to look like the output. And this is the output, and you have the points are the samples that you are giving to train, and the color is the prediction that the model is giving. So that's the idea of the neural network. You have many layers. Each layer has many neurons. Each neuron is connected to the ones that came before it and are going to be after it. And depending on the weights, the combinations are going to form these intermediate features that are going to represent something that can be useful, can be meaningful. Sometimes they are just, I don't know, nobody can really see what is there. But it gives good predictions. So this example, remember, I have something that already looks like what I'm going to predict. So let's say I'm going to predict yield, and I already have a variable that has a 0.9 correlation with yield. So the model is smart enough to pick that one that has higher correlation. That's the first one that is going to have high weights, and it's going to start predicting using that one. And that's an important thing that I'm going to show more later. But for images, for example, imagine that I have a data set with black dogs and white cats. So I'm going to train my model to predict what is dog and what is cat. It's always going to learn what is easier, and it's much easier to learn what is black and what is white than what is a dog and what is a cat. So that is important to understand, and it was already mentioned earlier about the interpretability or explainability of the deep learning model, which used to be thought as a black box that nobody could really even try to understand what was there. But with some regulations and with some needs, many people have dedicated their work to understand them better, and that's important because you need to know if you are predicting based on something that can be extrapolated, can be generalized to other situations or not. So if I was training with white cats and I present a black cat, it's very likely that the model is going to think that it's a dog because it didn't know that a cat could be black, just as an example. But let's move on. So this, by definition, wouldn't be considered still a deep learning model. It's a neural network, but it has only 2 hidden layers. And that's a gray area. Some people say more than 1, it's deep. Some people say more than 10. So I would say we need a few more layers here to really consider it to be a deep learning. And so we are going to pick a more complex problem. Now I picked this one. It's a kind of spiral, and it's harder to represent that with the data that I'm using as input, right? There is no single variable that has a very high correlation to it, so I'm going to need to work on more complex combinations of those patterns to get something that is similar. And that's the idea when I have 100 variables and the highest correlation I have is 0.05 or something like that. Maybe it's just noise and there is nothing to be learned, but maybe there is something to be learned. And with a simple model, it's very hard to learn, but if I have something that can learn more complex relationships, then I have some hope to get good results. So you can see that now this one has higher weights, but all of them have higher weights than before. So I need more combinations. And you can see more difference between the intermediate layers here. You see here this one starts to look something, and then this one goes to this tree, and then you see how the weights go here and go, and finally that's the best prediction that I could get. One thing that I didn't show before, but this is the typical accuracy versus number of epochs that I'm training, so number of iterations of my model. And with this kind of problem and some regularization that I have, you see that sometimes it thinks it's good, and then suddenly in the next step, it's bad again. So that happens because one of the things, again, the model always tries to learn what is easier. And sometimes, from an optimization perspective, what is easier, it's some local minimum in that function, in that loss function that you use to train it, right? And it's there, I think it's around here, but it's just a local minimum. So if I try different hyperparameters, or in this case, if I'm just optimizing the parameters itself, there are other regions in that hyperspace that I'm looking for that are better. So it goes from a low to a high, and sometimes it's very noisy, but you have to make sense of it. And in the end, I got a prediction that you can see a lot of orange dots are in a place that are predicted to be blue, so the model couldn't really represent that complexity. And what I want to be very clear about is that complexity is also related to the variables that you are able to measure. So if you have variables that are very well correlated to what you are going to predict, even if what you are going to predict is complex, it's going to be easier for the model. But if you don't have any single variable that can explain a lot, then it's more likely that you need some model that is deeper, or it's more complex in some way. Just I really recommend you, whenever you have time, to try to play with this tool. It's very good to understand. It's much easier to start here than starting in Python. That's going to be the topic of Thursday. But you can see that I can add more hidden layers, so I can make the model deeper, and I can add more neurons in each layer, so I can make it more number of options here. And there are other parameters here. I can increase the noise to see how the model perform. So when we are talking about the parameters of the model, all these connections, they are learnable. So that's something that I present the data, and the model is trying to get closer to that data, so it's learning those parameters. But all these parameters that are on top here and that are around here, those are the hyperparameters, because those, the model is not going to learn by itself. You need to help him with it. And that's not an easy task, but we are going to talk more about it later. So that was the definition part that I think it's you have heard it at least 4 times today, so hopefully it's good. Now we are going to enter in some more specific terms for image analysis, right? And one of the things that I like to talk about also, because my background is not in genetics, so I'm an agronomist, but I worked with precision ag, and one of the things that I worked a lot is with spatial statistics. And it's nice because some of the concepts also apply to the image analysis. So I'm going to try to explain some things here. This is how a computer sees a very small image, right? In this case, you can think of it as a black and white image. The 1 can be the white and 0 can be the black, for example. And why I mentioned the spatial statistics thing? Because one of the things that we have to do all the time is with correlation and with spatial autocorrelation. So if I'm closer to my neighbor, it's more likely that the value is still similar to my value than if I go 5 blocks away from my neighbor, right? As the distance increases, the correlation decreases. So you can see that usually when I have a 1, I have more 1s around it than when I have a 0. And when I have a 0, I have more zeros around it, right? And the way that it works here is that everybody has weights with everybody, right? And if I try to do that with an image, so this is a very small representation. I have here just 25 pixels, but I don't know. Does anybody know how many megapixels does a common smartphone has nowadays? 12 million, 16 million, 48 million, right? 48 megapixels. So that's a lot of pixels. Now you imagine that you have this amount of pixels connected to another set of this amount, and you try to just do the multiplication, and most normal calculators are not even able to multiply the numbers. Imagine multiplying all those connections. So they need to come up with something better than just a dense connection, just using all the connections possible. And the best way that proved to work was to take into consideration the correlation, right? So if things seem that are closer are similar, let's try to share some of the weights. Instead of giving one weight for everyone, let's try to give weights for groups of pixels. And that's the main idea of a convolution. The convolution was something that already existed before. It's applied in classical computer vision, and it proved to work very well in neural networks, and then the name became convolutional neural network, because one of the operations, one of those layers, is not a fully connected layer. I don't have all the weights that possibly, all the relations possible. I have a set of them that are related by the correlation or by the spatial neighborhood of them. And the other thing that we are going to define here is this kernel or this filter. So those are terms that are used to describe those. And those are the weights. So those would be the parameters that the model is going to learn by itself. And that again comes from the classical computer vision. We have some types of kernels that were already used. For example, you know, when you take a picture and then there is a lot of things that you can do with the picture to make it look better. So most of those things are related to this. You apply a filter over the image and it's going to pop out the borders, or it's going to blur something, it's going to show better some details. So, for example, this pixel can be a line of 1, then of 0, then of 1. That is going to show you a horizontal border, or like this, that is going to show an X format. That is also traditional for people that worked with remote sensing earlier on. There was some kind of processing that were also used to remove artifacts, to pre-process the data, or to improve the quality. But it proved to work very well here. So let's see how it works. So this animation shows it working. I had those weights that were in the green box there, in the filter, and I'm going to apply this filter all over the image. So I'm going to, every time I'm going to change the position, and I'm going to do this matrix multiplication, one element-wise multiplication here. So I multiply one by one the weight by the input value, and I sum everything in the end. And the sum of all of those is going to get there in each one of those pixels, or that new pixel. So that's, I think that's from the whole talk, that's one of the most important thing to understand here. So this is a convolutional neural network. Convolution is the name given to this operation. So it's a moving window that you apply and you move, and you apply and you move. And that has a huge impact in the whole efficacy of the method. And I think that's something important for the whole genomic prediction part. Whenever you have correlations between variables, if you can share the weights, the results tend to be better, because you don't need to learn so many weights, because some weights are going to be shared. So again, imagine that I had this output with 3 by 3, and this input with 5 by 5. So that would be 25 by 9, right? That would be the amount of parameters that I had to learn just to get from here to here. Now I reduce those to just 9, because they are always the same. They are going to change the position on the image also. And another explanation is, imagine that you have a plant in the top of the image. And then you moved your camera, and now the plant is on the bottom of the image. But the relation of the pixels that make that a plant is still the same. So you don't need to have a different set of weights to match with a plant that is in top, in the bottom. So sharing the weights makes a lot of sense. Now, that is the very simple case in a 2D with just one filter, and you can have even simpler, just in a one dimension. And I have been using it especially for time series analysis. So when you have things in time, they also tend to be correlated. The weather today is more similar to the weather tomorrow than to the weather 6 months from now. So that also makes sense for time series, and there is a lot of examples of using those there. But here we are going to focus on the images. And the images, they are usually not just one layer. They are read by the way that they start with. It's usually 3 layers if you're working with RGB, or they may be 4 or 6 or 10, or in a hyperspectral imagery you can have 450 layers maybe. So you need weights for each one of the entrance layers, because you cannot assume that the weights can be the same for the green and the red channel, for example. And so that's actually what is happening when I'm developing a model with a convolutional neural network. So I have the weights for the green, for the blue, for the red channel, and I also usually have a bias term to account for some other things there in the model. So for each one, instead of having 9, actually I'm going to have 28 because I have 3 channels. And in the output, I don't need to have just one layer either. I can have many layers or many dimensions to that same layer. So in this example, I have a set of weights that gives that output, and I have another set of weights that is applied to the same input to give that one. So that's actually how it works, and you can see that there is a lot of matrix multiplication, right? I'm multiplying and over again, and that's where it comes to the other big leap in deep learning, is the use of the GPU that we commented earlier. So graphical processing unit. The GPU was developed mostly for gamers, for people that play games that require a lot of renderization. So making something that looks like 3D in 2D in real time. For people that are used to AutoCAD or other things like that also, because when you need to convert something that is a vector into something that is a 2D raster in your screen, they are very useful. But they happen to be also very useful for deep learning because they are very good at doing matrix multiplication, linear algebra in a way that is very fast and very efficient. And we are working nowadays with most computers with 6, 8, 12, 16 cores, right? That's the amount of cores that you have, either physical or virtual, and you can use that to parallelize and to run things faster. But with GPUs, we can have more than thousands of cores in a very small piece of equipment that is also very energy efficient, and that enabled this to happen much faster. So what you have to do is to run all these multiplications, you get that, you get all the way to your prediction, and then you go back and you update your weights, right? And that's how it learns. That can take 100 times more in a CPU than it takes in a GPU. So that is the amount of gain in speed that we are talking about thanks to the GPU. Just another operation that it's very common in the deep learning for images. It's what we call max pooling. So previously, it was shown what is a ReLU or ReLU, rectified linear unit activation that takes an input and the output is non-linearly correlated to it, right? So that enables the model to represent complex non-linear interactions. That is also used in convolutional neural networks, but another one that has both, that has two things that make it efficient is the max pooling. So what is a max pooling? I take the max value of a small window, so usually 2 by 2 or 3 by 3. So that's a downsampling operation, so I have an image that is very large, and I want to reduce the resolution. Because the idea is you are going to do you're going to reduce the dimensionality of it, because if I take every pixel, it's too much. So I reduce the dimensionality, and instead of just averaging, the average would be something linearly correlated. So I take the max, and that it's that also adds some non-linearity to it and makes it more able to explain different things. So that is something that we are going to work more on Thursday. But the idea here is you do that and then you repeat the convolution. And so in the end, you are with an image that is much smaller, but has the features, something that is much richer in information than just the pixels. And that's the representation of a typical convolutional neural network that you can find. So you have the input, and you can think of the image, usually small. Even a good GPU cannot accommodate an image that is like 16 megapixels, so you need to either downsample it or work with parts of it, because it's still a lot. Then you can apply some convolution, you apply a max pooling, so you reduce the resolution. But you see that I'm reducing the resolution, the spatial resolution of that image, but at the same time, I'm increasing the number of bands that I have here, or the depth of each layer. So instead of having just RGB, I'm having RGB and or something else that I derivated from that. You can think of it as a vegetation index, or an index of borders, or an index of texture, something like that. And the whole point is you are reducing the spatial and getting an information that is more rich. And then in the end, you do a normal neural network where you have those features that are more closely correlated to what you want to predict. So that's the idea. This convolutional part is making the life of the model simpler. It's making it easier for it to learn, because it's trying to get something that is correlated. In the same time, because it shares a lot of weights, it's not so hard to learn. Because if you are going to train each one of those weights, you are probably going to need billions of images. And that's not feasible in the time that we had. So that's the general structure of a deep learning model using a convolutional neural network for something that has only one output here, right? So let's say it's a classification, it's either cat or dog or something like that. Keep in mind that this can be many classes or can be different outputs. Networks are very flexible. So for example, I can take something from here and make an output and then keep going and take another output. In some cases, and that's also what we are going to work with more, I can go all the way here and then I repeat the reverse of the network, and then in the end I have another image, an RGB image with the same resolution or with more bands, but that is again much easier to be understand by a classical computer vision algorithm, for example. So in the end I can have an image that has the prediction for each pixel instead of having just one output, and that's I'm going to show you. I think that was also discussed a lot. So we have the parameters that the model can learn, and we have the hyperparameters, and all of those play a role in model tuning. In how do you tune your model to be better, especially to be better in a situation that you didn't test it, or in a situation that it's a real application, right? And when we work with linear models or some of the classical statistical models, more often than not, we have underfitting. So we have a model that cannot really represent all the complexity of that data, right? And that's why deep learning become important, but we have to be careful to avoid this. This is good. This has a good application. So how do I use overfitting in my favor? Well, overfitting means the model is way too complex. It's able to memorize every single bit of data that I'm giving to it. And that also probably means that at some point it's going to fail horribly because it didn't learn anything that is meaningful. It just memorized the data. But what is the good part of it? Usually the recommendation, especially with complex models, is you want to be sure that first, all your code looks right. Sometimes you made a very silly mistake, and that is going to cost you a lot of time just because your code is wrong. And so one way to make sure that your code is right is showing that you can overfit. The other thing is, if your model can overfit very well, that means that it's complex enough to really fit the data. And then you work backwards to get somewhere in the middle. So you use regularization, like the dropout that was mentioned, and there are other techniques to get a good result from there. So I already explained this, the idea of the hyperparameters. The less hyperparameters you have and more parameters that the model can learn, the better, because you don't need to do it by yourself. Examples, number of layers, number of nodes in each layer, and one that I didn't mention, the learning rate. So that's how fast you update those weights based on the direction of the errors that you are getting. So if you're predicting too low, you are trying to optimize it to predict higher. Maybe if you update it too fast, you're going to predict way too high. So it's some things to keep in mind. Those are the things that I already mentioned also. So that's important to understand that mainly the convolutional part is doing reduction of the dimensionality of the data, but you need to understand what is being extracted from there, because one way to reduce the dimensions is just take the average, and that's the example of the black and the white, because the average is going to be fairly different. But the color is not a very robust feature, because if I change the camera, the illumination is going to fail. So it's good to understand what the model is getting to see if it's robust or not. For example, texture is more robust, size, it depends. If it's from a drawn image, it's usually not very robust. The position, again, it's usually not robust because I can rotate the image and things like that. And those are all the things that you need to ask yourself if those features are robust to these things that can happen, that normally will happen in the image. Now we go to the interpretability part, and that's a hot topic. Many people are doing their thesis on that. I find this book, I read it recently, and it's very good. And also the language, it's good. You have some reference to other books there, so I recommend it too. And now I just show some examples of the idea of what is a feature or a high level feature, a rich feature, in comparison to a more simple feature. So this is usually what the model learns in the first layer, and you can see that the filters here are mainly highlighting borders in different directions, things like that. When you go to a more intermediate level, it's learning what is an eye, a nose, an ear, so parts of a body. And then in the third layer, it's actually learning what is a face, and it's learning to recognize different types of face. So that's the idea of the feature extraction and the complexity of what the model can learn. So if I have a model with just one layer, that's what it can learn. But if I want to detect persons with a high degree of accuracy, I need some model that can do it, can deal with the complexity of it. If you search for this in the internet, there are many examples. Some look amazing, something that many people wouldn't be able to draw, but there are many examples. Another one, just so you have the edges here, you have some texture, some more complexity, then you have some patterns, now you have parts of objects, and then you have finally here the objects as you go deeper and deeper. And when we talk about plant phenotyping, I'm not sure that you need to go so deep sometimes, because sometimes the thing that you want is not that complex. You don't have as many classes to predict as in these examples, but it's good to understand what the network is doing. Okay, so now we are going to talk a little bit about data. And data is still a problem. Even though we have big data, we have a lot of data, we can take, I don't know how many thousand images in a day. And so there should be no problem with data, right? Wrong, because these methods, they are supervised methods. So I don't need just the image, I need the ground truth, or I need the thing that I want to predict. And that is the costly part. It's easy, it's cheap to take images, but it's costly to annotate those images to really mark there what I want to predict. So the idea of one of the things that you can do is you can do data augmentation. So you take your same image and you try to apply any transformation that makes sense for that kind of image, and you keep the same output. So this is an example. I can scale, I can rotate, I can blur it, I can change the illumination. Another example with the cat, I can rotate, crop in different positions. So those are all techniques that can help a lot on getting better models that are more robust to these variations, because they are going to happen, without the need to just collecting more and more data and labeling them, because that's expensive. If you want to learn more and you want to practice in the real world, there are some challenges that already have the data for you and the ground truth for you, and even some models as examples, so you can work from it. Kaggle is one of those. This is a very famous platform. So they have, for example, Facebook is going to put a challenge there with a prize of 1 million. And that's a cheap way for them to hire developers all around the world to solve the problems. So that's common. There are some examples. So this example of seedling classifications, I think it's from a research group in the Denmark that has this example there. There are some kernels notebooks here that you can use to start learning. This is an example more related to phenotyping. So this comes from the International Plant Phenotyping Network, and they have a few data sets there, mostly in Arabidopsis, tobacco, these plants that are used as model plants, and those are all annotated, and you can use them to train, to practice. Now, the real challenge. It's actually easy, or it's not that time consuming when you have the data ready, especially for images, and you just need to optimize the hyperparameters and train models. That's actually, you know, what many people think, that's how a programmer spends his time. But the reality is that really doing the code is the part that takes less time. Experimenting to optimize it, to get it right, takes more time than that. But what really takes time is getting the training data ready. And it has to be good training data. So if you want to do something with an image and you just take an intern that is there for the first week and you help him, I don't know, give him instructions from 10 minutes and say, do it, the chances that the data is going to be very well annotated are not that high, and the model is just going to learn what is in the data. Remember, it's a data-driven model. So if the data is not good, don't expect that much from the model. So this is important for the ones that are planning to do a thesis on deep learning. Remember to plan your time accordingly, because it's probably going to take more time than you think in the beginning. For the annotation part, I'm just going to give a suggestion that I think it's very easy to use, is this VGG image annotator. VGG has a very large data set that is used for benchmarking in many areas also, but they have this tool that is just a HTML web page that you can download, and you can open your browser and you can import the image, you can annotate in different ways, you save it, and then you can use in your Python, whatever. It's really easy to use. Just some examples, annotating to count corn here, and for the people that are in GBank that helped me to prepare the mini course, that's something that we did and we are going to do again. And then just an example of how, in the end, what I can extract from that. So this has the prediction of the rows, the crop, and I cannot really see it much, but I have one color for the center of the crop, so to make it easier to count, and then I have one other color for the leaves, and I have here some weeds. So it's That's another way to do things. It's a pixel-wise prediction. Instead of predicting just one outcome, I can predict pixel by pixel. And then just to show there are different objectives, and that's also important to have in mind. This most simple one and the most used is this one, which is classification. Is that a cat or not? I can have this with localization. So, okay, it is, where is it? I can have more than one object, so I need to find where they are, what can be considered an object or just background, and then I can label what they are. And in this is pixel level instance segmentation. So I know this is a cat, and I know that this pixel is also a cat, but it's another cat. It's not the same cat. And that requires much deeper networks, right? So those are where these deep learning techniques have been very successful, because those are complex things to do with conventional methods. This is one of the examples from the CVPP that I showed before. So I have the original Arabidopsis here. I have some leaves detected. I can do the semantic segmentation, so taking what is background, what is leaf. And this is the hardest to get, probably, which is the instance level segmentation. So pixel by pixel, it's a leaf of Arabidopsis, but is the first leaf or is the fifth leaf? So that's where we are at with deep learning. Now, just to show, I can try to play again, but this is soybean. Those are experiments in Illinois. And that's just to show some of the work that I did recently there. So this is a sequence of drone imagery that is about 40 days in the video, and you can see the plants getting mature, and then in the end, I'm going to show the prediction of the maturity date. So that's using deep learning, and that's a complex model because it has the spatial aspect of it, and it also has the temporal aspect of it. So getting the image right, in the right position, and then building the model to take into consideration the time. It was challenging, but it works very well. So I can predict maturity within 2 days of the actual date that they went to the field and scouted for it. And from the same project, just showing some examples. So these are some of the images stacked together. So every column here is a date that the drone was flown. The red lines in each of the plots, it's the date that the model predicted the maturity would happen. And the blue ones are the ones that they had some check plots, some materials that are already in the market, that they know the maturity group, and they are here together, so you can see it's doing very well. And there are other examples here. It's a little small, but you can have an idea. This is what we are going to use mostly on Thursday. So software for it, mainly for image analysis. There are some ways to work with it from within R, but Python is so much more efficient that usually most of the things are done in Python. Even if you do in R, you use either Keras or something from within it. Anaconda is a good package manager to have Python in. I use more PyTorch because most of the high performance models are implemented in PyTorch, and what I'm working is to get those into the edge, to have those in real time also, and for that I need a lot of performance. And then the OpenCV and PlantCV that are more traditional libraries, especially to organize the data. It's very interesting. And the Google Colab platform, which is just a platform that Google made available that you can log in with any Google account, and you can have a GPU for free to access and to test many things there. So just to conclude, why is it that deep learning is so famous right now? So we had a lot of hardware improvements, all the GPU aspect and the computing power in general. We have a lot of software improvements, so all these libraries that became publicly available and a lot of people collaborating on it, all the social media, autonomous car, many companies put a lot of money on it and then made it publicly available. And all those open source tools enable you to start using it without any investment. There is also a lot of web courses that you can, or classes that you can take and learn more about it. And finally, because you can train your model using a lot of techniques like the data augmentation that I showed, that enables your model to be more scalable. You can actually deploy it in the field in different illumination conditions, and it's much more likely that it's going to work if you did a good training with good data than it was with traditional computer vision that you tested it, you had to optimize many parameters also. You still have to optimize the hyperparameters. But before, when you went to the field, okay, now I need another set of parameters. Now, because the model is so complex that it can learn underlying things, it's able to really learn what is able to be replicated out in the field. So with that, I'm glad to take any questions, and thank you for your attention.
The session is open for questions. Anyone? I would like to ask you, in your opinion, when do you think these tools applied to new technologies will be widely available in breeding programs as a routine use, like drones or other new technologies? And what are the main limitations for not happening yet?
Okay, great question. And it's hard to answer. So the tools in general, they are available. You can get them, and they don't cost that much. I think one interesting thing from the first presentation about auto machine learning is that the tools are available, but you mostly need an expert to really be able to use the tools. So they are there, but they are not that user-friendly yet. So I think that is what it takes to make it really available to all the breeders, is more platforms or more solutions that bring this to a more easier to understand and to use. Also because people don't have time usually to invest on learning or testing too much, so they want something that's ready. And I don't know of any tool that is really ready to be used in production in the breeding program.
Anyone? Thank you.